Okay, we had left off, we had just introduced the idea of an indicator, and we said an indicator is generally a weak acid that changes color when you pull the H plus off. And usually that's going to happen right around the pKa of that indicator. So methyl orange, for example, appears orange right around a pH of 3.8, which is pKa. But you go down a little bit from there, and it appears red. You go up a little bit from there, and it appears yellow. And notice the yellow just extends. Anything above about 4.5 is just going to be completely yellow. So if you want to distinguish between a pH of 7 and a pH of 8, is methyl orange going to be very effective? No, because it's going to be yellow either case. If you want to distinguish between 1 and 2, is methyl orange going to be effective? No, because it's going to be red either way. So usually they're effective within about plus or minus 1 pH unit of its pKa. Beyond that, they're not useful. So when you're doing a particular experiment, you usually want to select an indicator based on what pH you're trying to indicate. And so the good news is we've developed lots of different indicators, and we know exactly where each one changes color. So you want to always use an indicator that has a pKa within about plus or minus 1 of the pH you're trying to indicate. Now, we are kind of ingenious in that we've been able to come up with certain combinations of indicators that we can put together and make solutions that will indicate a broader range of pH. So those are called universal indicators. Universal indicator is not a single compound that changes color multiple times. It's a mixture of compounds that changes color multiple times depending on the pH. So you can get a solution that will indicate a broader range, but sometimes you want to choose just a specific indicator. So later this week in the lab, and then in the next couple of weeks, we'll be doing it again. We'll be doing some titrations. And for titrations, a lot of times you use an indicator to tell you when you've reached the equivalence point of the titration. And so it's important to choose an indicator that's going to change at the right time. So very quick, simple multiple choice question. You're making a solution with a basic salt and want to make sure the pH does not go above 9. Which of the following indicators would you use? Yeah. The great thing about these indicators is a lot of them have 5 consonants in a row, which is kind of rare, right? So phenolphthalein and thymolphthalein. Usually we treat the pH in the middle as being like silent, so we'll say like phenolphthalein. But yeah. All right, so in this case, the best choice would be phenolphthalein. Why not thymolphthalein? I mean that has a pKa of 10. That's going to change at 10. So by the time it changes, you're already past 9. So if you want to make sure it doesn't go above 9, then phenolphthalein would be a better choice. All right. So that's the idea. Years ago, we didn't have very simple ways to measure pH, which we do now. So indicators played a much more important role in the past before the advent of modern digital pH measuring devices that do make it a lot simpler. But if you've ever tested the water in a fish tank, tested the water in a pool or a spa, then you probably used a simple indicator. For pools, it's usually something called phenol red, which changes somewhere between 7 and 8, because that's usually the range where you want pool water to be. All right. So on to the next part. What I'm hoping to get through today is discussion of buffer solutions. So in a lot of cases, you want to make a solution and you don't want its pH to vary very widely. Can you think of any reasons why you might want to make a solution where the pH stays roughly constant? All right, so in terms of water, drinking water, maybe, although we usually don't want to add too much buffering stuff to drinking water because then it'll taste bad. But water in a pool or a spa, you don't want the pH to change too widely, so you want it to be somewhat buffered. Can you think of any other situations where you might want to use a buffer solution where the pH stays roughly constant? All right, in a situation where you're running a specific reaction and you want the pH to stay constant so it doesn't change the reaction rate. Specifically, what kinds of things might be very susceptible to changes in pH? Any ideas? Proteins, biological molecules. Yeah. If you're doing biological experiments with live cells, then usually you do those in a buffer solution because any change in pH by a unit or two can kill them and can also change the enzyme activity. So buffer solutions are important for that reason. There are lots of natural buffers. We all have multiple buffers in our own bodies, including our blood. If our blood pH changes by a unit in either direction, then we're probably dead. So it can be really important to keep pH constant. So we want to have an understanding of what a buffer solution is, how we would make one, and then how to choose specific buffer solutions for specific applications. So how do we make a buffer? Well, let's think about it. We want a buffer when we add a source of H plus to it. We want something there to soak up that H plus so that it essentially doesn't make the solution more acidic. And if we add a base to it, we want something that produces OH minus, we want something there to give that OH minus H plus so that it becomes water. All right? So what kinds of things could I add to a solution that would soak up extra H plus in the solution? What do we call things that soak up H plus? Bases. So we would want in a buffer solution to have a weak base there that can grab extra protons that are added to the solution. And then if we add extra OH minus to the solution, we want something that can give it H plus. What do we call things that give H plus away? Acids. So essentially a buffer solution is going to have a weak acid and its conjugate base. It's going to have a weak acid base conjugate pair. You know what? I'm going to just cross out this sentence here. This phrase, weak acid and its conjugate base, must contain a weak acid / weak base conjugate pair. The reason I'm changing that phrase is sometimes people think, oh, a buffer should have a weak acid and its conjugate base. And then they say, oh, what about a weak base and its conjugate acid? Would that work? And the answer is yes, because those two are the same thing. So I don't want you to think that the phrase weak acid and its conjugate base or weak base and its conjugate acid are different things. They're the same thing. So a weak acid, weak base conjugate pair. So when you add a base to the buffer, remember a base is an H plus acceptor. What'll happen is the weak acid molecules say, no, don't take H plus away from water. We'll give you the H plus that you want. All right? So when a base is added to the buffer, the weak acid donates H plus to it. So the base doesn't need to take H plus from water. And if we add acid to the buffer, we add a source of H plus to the buffer, the weak base is going to come along and take the H plus from the acid. Say, no, no, don't give the H plus to the water. Give the H plus to me. So to make a buffer is pretty simple. You just put a conjugate pair in the solution. And now, if you add acid to it, pH might change a little bit, but not a lot. If you add some base to it, pH might change a little bit, but not a lot. Question? The question is, does the conjugate pair ever have an acid-base reaction? Here, I had a blank slide right here. So let's think about a conjugate. Let's name a conjugate pair, a weak acid, weak base conjugate pair. HF and F minus. All right. So example, weak acid base conjugate pair. HF and F minus. So the question was, do those two ever react with each other? And the answer is yes, they react with each other all the time. What are the products when HF and F minus react with each other? HF is going to give away its proton. So what does HF become when it gives away its proton? F minus. And F minus is going to accept the proton. So what does that become? HF. So, yes, this reaction happens all the time in the solution, but it has no effect because the products are the same as the reactants. So yes, this is happening constantly. These molecules are constantly exchanging the proton, but it has no effect. But it's worth exploring all these things. So these questions are going to come up throughout this unit, and on problem set 19, you do a lot of thinking about what happens when X reacts with Y. So I want to encourage you, anytime that thought pops in your head, wait, don't these two things react? Write the chemical equation then and ask yourself if it's important. So in this case, yes, this chemical equation happens. No, it's not important because it gives you the same thing you had before. So when you have a buffer solution, you have the weak acid and its conjugate base in the solution all the time. All right, so just to put it another way, in a buffer, we said it's a weak acid, weak base conjugate pair. They each have a role. The role of the acid is to buffer against added bases. And the weak base buffers against incoming acids. So, so students just asked the question, isn't there a limit as to how much they can buffer? And there is. If you look a couple slides ahead, there's a slide entitled buffer capacity. So, if these are your defense forces, the weak acid is your defense against an incoming base, well, there's a possibility that you could add so much base that it would overpower the weak acid there. Same thing, the weak base is your defense force against incoming acids. You can add enough acid to overpower it. So no buffer works forever. Buffers just work within a certain range. So all right. So the question is, what if there's a base that's added and it reacts with the weak acid? All right. So again, I'm going to go back to my blank slide for a second here. So let's say I have a buffer that's got HF and F minus in it. If I add an acid is a source of H plus. All right. Whose job is it to meet that acid? The F minus. So this is the reaction that's going to happen. F minus plus H plus makes HF. So essentially, when I add excess acid, it'll use up some of the F minus and it'll make more HF. All right, so the question is, there's no such thing as pure H plus. I can't just add pure H plus. I'd be adding a compound like HCl. Well, if I add HCl, then now there's going to be more chloride in the solution afterwards. The chloride just acts as a spectator ion. So when I talk about adding an acid to the solution, really, all I care about is the H plus part of it, of the acid, because that's what's going to affect the pH. The other ion is just a spectator. But it's an important question to consider. If I add OH minus to my buffer, whose job is it to go out and greet the OH minus and fend them off? HF. So what happens? Well, HF comes out and greets the OH minus. And what's going to happen? I'm going to make H2O and more F minus. So essentially, by adding an acid, you convert your weak base into its conjugate acid. By adding a base, you convert your acid, the HF, into its conjugate base. But the point is, by doing this, you're not allowing it to just release more H plus or more OH minus directly into the solution. So the pH doesn't change as much. All right. I forgot when I started this discussion, I forgot to bring up the most common example that many of you might be familiar with of a buffer solution. How many people wear contacts? Some of you. All right. Do you put your contacts in water at the end of the day? Oh, you have disposables. All right. Yeah. So if you don't have the ones you throw out every day, then every night you've got to take them, put them in a case, and you've got to put some buffer solution in it. You don't just put tap water in it. That buffer solution serves two purposes. One, it does have some antibacterial agents in it to kill, microbes that you don't want to grow in your eye. But the other one is it's a buffer solution. It keeps the pH specifically where you want it. Yeah, we can't just ignore the fact that there are microbes living all around us. So the question is, what would happen if you just put it in tap water? Has anyone ever done that? All right, so if you drop your contact and you wash it with water, how does it feel when you put it back in your eye? Okay. It stings. Your eye's pH and the tap water's pH are not the same, and your eye is sensitive to that. Um, I don't know the ideal pH of the eye, but the idea is it doesn't feel good to. Same thing when you swim in a pool. If the pH of the pool is off, the way you notice it first is your eyes, um, probably. All right, so this is the idea with buffers. We have a defense force against incoming acid. We have a defense force against incoming base. So ideally, if we want a buffer to work equally well against incoming acids and incoming bases, right? If we have a situation where we're not sure what might fall into the solution, then what we want is equal concentrations of the acid and its conjugate base. So equal concentrations of both the weak acid and the weak base. Question. So good question. The question is if you're making a buffer, and let's say you make a buffer with HF and F minus, couldn't there be possible side reactions where the F minus reacts with something? And the answer is definitely. So when you're choosing to make your buffer solution, you try and pick uh, a conjugate pair where neither member is actually going to disturb the other things in the solution. You know, in any biological solution, HFF minus, this would be a terrible buffer solution to choose because it would have all these negative effects. So yeah, that is another consideration. Like when you choose a buffer, all right, what weak acid, weak base conjugate pair can I select that will not have other negative consequences? Definitely. Yes, that's the question. All right. So the question is, why is equal concentration so important? And it's not so important. Um, so here, when I say an ideal buffer, what I mean is a buffer that works equally well against incoming acids and incoming bases. That's not always important. Um, so, for instance, in your blood, there's a lot more processes, biological processes that release acid into your blood than processes that release base into your blood. So it turns out your blood buffers better against excess acid than it does against excess base, and that's just a kind of an imperative that it needs to. So this isn't always the case, but usually when you start to design a buffer, usually this would be your baseline. Let's see if I can make a buffer with equal concentrations of both, because then it'll work equally well in both directions. Uh, so my question is, if you have equal concentrations of each member of the conjugate pair, so equal concentrations of the acid and the conjugate base, have we seen that situation before? If you look back at the notes from last Thursday. Have we encountered the situation where we have equal concentrations of acid and conjugate base in a solution? All right, yeah, we saw a few situations where if we have equal concentrations of HA and A minus, then pH is going to equal the pKa. So in other words, this is going to be another situation where the pKa of my acid is going to be right around the pH of the buffer solution. And we'll prove this to ourselves on the next slide. All right. So I'm going to solve this by applying a Rice chart. And then I'll talk about how we could just use the HH equation as a shortcut. So a solution is prepared by adding 0.1 mole of HCN and 0.1 mole of NaCN to 1 liter of water. Again, this would be a terrible buffer if this were a biological situation, because cyanide kills almost everything. But as a hypothetical exercise, we can calculate, all right, what would the pH be? There are actual organic reactions that you would run in this kind of mixture of HCN and NaCN. So it's not like outside the realm of possibility, but it wouldn't be a biological situation. So when we're answering this question, what is the pH? In chapter 18, we constantly just focused on doing what? How do we determine the pH when we have a solution with a weak acid in it? Look back at the headings on chapter 18 notes. It's at the top of every page. Rice charts. Yeah, rice plus acid equals fun. So I'm going to set up a rice chart, and I'm going to deal with an equilibrium. I need to have an equilibrium that contains HCN and then NaCN. Well, one thing I'm going to do to NaCN, hopefully you're starting to see this, when we deal with acids and bases and we see an ionic compound like NaCN, what should I mentally do to it? Break it up, all right? And when I break up NaCN, I get half that I'm interested in and half that I'm not. So this breaks up into Na plus and Cn minus. And which half of that am I not interested in? Na plus. This is a spectator. It's just a bystander, a passive bystander, not an active bystander. So I'm going to ignore the Na plus. I'm just going to focus on the Cn minus. So I need an equilibrium that contains HCN and Cn minus. Can anyone think of a simple equilibrium I could write that deals with HCN and Cn minus? Well, what can HCN do? Ionize. It can dissociate into H plus and Cn minus. Yeah. Do I know the K value for that reaction? What would I call the K value for this? Ka, because it's an acid dissociation. I could look at the blue sheet to get my Ka value. For this reaction, it is 6.2 times 10 to the negative 10th. All right. So now I'm going to fill in what I know. What's the initial concentration of HCN? 0.1 molar. What's the initial concentration of H plus? 0. What's the initial concentration of Cn minus? In chapter 18 it was 0, right? If you've been working on problem set 18, you've done a lot of rice charts where, you have an initial concentration of your acid and then 0 and 0. This is not the case. Here I have 0 H plus, but how much Cn minus? 0.1. All right. Bless you. So just like the rice charts that we do on problem set 18, except instead of having 0 for my initial value on the right side, I now have a non-zero value there. But the change is still going to be the same, minus x plus x plus x. So I get 0.1 minus x at equilibrium, x, and 0.1 plus x. All right. Tell me about my k value. It is very small. All right, when my k value is very small, that saves me a lot of trouble. Because 0.1 minus x is 0.1. 0.1 plus x is 0.1. Ah. So now I get Ka equals, remember, concentration of H plus times concentration of Cn minus over concentration of HCN, which is going to equal x times 0.1 divided by 0.1. Well, I think I can do that math in my head. 6.2 times 10 to the negative 10th equals x. So then x is the concentration of H plus, so the pH is going to be the negative log of that. And the negative log of that is something like 9.3, 9.21. All right. So we can solve all these questions using rice charts just like we've done. So this is, if you get familiar with rice charts, you can just keep using them over and over. Now there is a shortcut you can use in these buffer situations, because you know the concentration of the acid and its conjugate base at equilibrium. Because essentially K is always going to be small, and so X is always going to be negligible. We could have shortcutted directly to the HH equation, which was, remember, pH equals pKa plus log of concentration of conjugate base over concentration of weak acid. And in this case, since we had equal concentrations of Cn minus and HCN, what does that imply? pH equals pKa, which we said a moment ago. So if we took the pKa of HCN, we'd find, oh, it's 9.21. So the pH here equals the pKa. So for determining the pH of a buffer solution, you can, if you choose, skip the rice chart, just use this HH equation and get your pH. It's a helpful shortcut. I am not advocating that everyone must use the shortcut. I personally never use the shortcut because I liked the broader technique that works all the time rather than the narrower technique that only works for a buffer solution. So I'm always going to write the rice chart. When you look at answer keys, you'll almost always see the rice chart written out because I just prefer it that way. But you are welcome to approach it either way. What questions do you have? All right, let's do another example. This is probably a more realistic buffer that you might use in a lab. Buffer solution is prepared by adding 0.8 moles of NaH2PO4 and zero point 0.4 moles of Na2HPO4 to 2 liters of water. What is the pH of this buffer? You go ahead and try and come up with an answer. I'll go ahead and try and come up with an answer. Well, actually, let me guide your thinking a little bit before you start. What's the first step here? I have to figure out an acid dissociation that I want to write as my reaction. I have to figure out which dissociation I'm analyzing. So what do I have to do to each of these compounds before I can do anything? Break them up and get rid of the spectator. So I'm just going to cross out the Na and put a minus. So I have H2PO4 minus. And then cross out the Na2 and make this a 2 minus. So what reaction am I analyzing here? H2PO4 minus, dissociating into H plus and HPO4 2 minus. Where am I going to get the K value for that reaction? From the blue sheet. Specifically where? The polyprotic. Yeah, you're going to look in the polyprotic acids. And are we dealing with the first dissociation, second dissociation, third dissociation? This is the second dissociation of what acid? H3PO4. So I'm going to look up Ka2 of H3PO4. And that'll give me the Ka value for this. All right. So see what you can do from there. All right, I think the pH should be 6.9 something. Is that 6.991? All right. So the pH is 6.91. Two ways you could have gotten to that. You could fill out the Rice chart, set up the equilibrium expression, solve for x, and then take the negative log of x. Or you could have used the Henderson-Hasselbalch equation and, get the same result. So would this buffer be better at buffering against excess acid or at excess base? This has more of the acid, more of the conjugate acid, so this would be better at buffering against base. And notice, because it has more of the acid, the pH is going to be a little bit below the pKa. If you have a buffer that has more of the conjugate base, that pH is going to be a little bit higher than the pKa. So the question is 6.91 drinkable? Yeah. As far as drinkability, I mean, if you drink Coke or orange juice, you're drinking things at like pH of 2. So yeah, definitely 6.91 is drinkable. Phosphate isn't necessarily going to hurt you, so this would be fine. Coke has a pH of 2. Yeah, Coke is quite acidic. Question. So the question is about toothbrushing, and if you drink something really acidic like orange juice or coffee can be pretty acidic, red wine. So they say don't brush your teeth right afterwards. Wait a little while, because brushing while there's the acid there can wear away some enamel. Now, as far as toothpaste goes, toothpaste has fluoride in it, but it's not particularly basic. Fluoride is a very very weak base. So that fluoride isn't necessarily going to buffer against the acid very well. What you could do, let's say you drink orange juice and you want to brush your teeth right away. You could gargle with some baking soda solution. And so the baking soda would neutralize the acid, right? And then you could spit that out, and then you could brush your teeth. I think that I'm not a dentist. But from a chemistry perspective, that should work, I think. Yeah. Another question. So the question is, the reason why this particular solution would be better at buffering against base is that there's more of the acid form. Yes. So 0.4 molar versus 0.2 molar for the base. There's a little more acid to buffer against added base than there is base to buffer against added acid in this case. Yes. So the question is, if you follow my advice and you drink Coca-Cola and then you gargle with some baking soda solution, would it foam up? It may be a little, yeah, sure. Because baking soda, when it reacts with an acid, produces carbonic acid, which then decomposes, produces CO2. That's why baking soda and vinegar make volcanoes. You do that as a kid. So yeah, it would probably bubble up a little bit. Question is, how would it feel? Probably tingly. I don't know. Just like kind of like drinking soda, essentially, because that's what you're doing when you drink soda, is drinking water with carbon dioxide bubbles coming out of it. All right. So I guess we'll leave this to next time. But what we're going to do next time is actually we'll start class by doing a problem from problem set 19. So we'll get that out of the way. But it's going to have to do with, we're going to do the math to prove to ourselves how a buffer works, and then to think about, well, how would you overcome a buffer?